today's machine learning crash course. Today we are going to talk about, actually we want to continue our discussion about linear regression models, and today we are going to talk specifically about the bias variance decomposition. Actually, we will see this in the chapter of linear regression model, but we can generalize the results of this discussion for other models also. We have seen that in maximum likelihood, or equivalently when we want to have least square error, if we have complex model, we are very prone to overfitting. Then we have a limited data set, right? So if we have complex model and our data set is limited, then we are going to overfit on our data set. And this is actually, we don't like overfitting because it means that our generalization performance is really poor. If you remember that if we plot the test error and training error based on model complexity, if this is complexity of model, for example, in an example of polynomial fitting, it could be the degree of polynomial, and this is the error. Then the training error will be something like this, probably. And so this is a training error. When we make our model more complex, the training error will decrease, but the validation error is something like this for test error. So as you could see, there is an optimal complexity in which the training error and validation error are actually good, but when we increase our model complexity, then the model will overfit, and so the test error will increase. In here we have overfitting, and it is because our data set is limited, but our model complexity is so high, so in this case we have overfitting. For preventing overfitting, we saw that one way is to introduce some terms in the loss function, for example L2 regularization for the model, in which we actually, if for example this is the squared loss, we added this term to the cost function to reduce the variance of the weights. So in this case we have seen that with choosing the optimal value of lambda, suitable value of lambda, we will have a good generalization for the model. So but the point is that choosing the lambda is actually not an easy task. One way for determining lambda was to using k-fold cross-validation or actually holdout cross-validation, holdout validation to determining the suitable value of lambda, but it could be computationally expensive. So actually we want to derive another way to determining lambda automatically. But before that, let us to introduce some terms, and first we should recap what we derived in the last sessions. If you remember, the expected value of loss was the integration over the loss value times probability, the joint probability of x and t, dx dt. And we concluded that if we choose a squared loss as the loss function in here, the optimal decision making is to set the h of x, which is the optimal prediction for x, equivalent to the expected value over t given x, and that is actually the integration t, the conditional probability t given x dt. Okay, so we want to actually a little manipulate that to give some insight about this term more. Okay, for this, we have seen that we could write it in this way. When we have a squared loss, it could be y of x minus h of x squared plus the integration h of x minus t squared times joint probability dx dt. And we call this intrinsic noise because it does not have anything to do with actually our model, which is a y of x. It is not related to y of x. It is actually related to the target values, which are these are the training data and the true function of the training data. So this is the intrinsic noise, and the first term just depends on the model, which is y of x. And we know that if we have unlimited number of data, then we could actually calculate h of x with desired accuracy from this equation. But the problem is that we just have limited data set. We just have n number of data. So the severe problem in machine learning is that we don't have much data. We don't have infinite size of data. We have limited data. So if we model h of x with y of x and parameter w, okay, if we use the Bayesian approach, the Bayesian perspective point of view, It means that after applying Bayesian approach, we have the posterior distribution over W. Okay, this was the Bayesian perspective. Okay, while in frequencies approach, we will end up with just a single estimate or point estimate for W based on data set. So for very particular data set, let's call it D for a specific data set, the error is simply just this. And this is just for actually one data set. We could take the average for all of the data sets to derive the average error. But before that, we could add and subtract the term that help us to understand this equation more. So we actually add and subtract the expected value of y. This is the expected value over all data sets, and this is the prediction of model on a specific data set, plus expected value over all data set y of x minus h of x squared. Okay, so now we could take the average over all of these data sets. So over this, we could take an average over all data sets. So we have the expected value over d y of x and d for specific data sets minus h of x squared is equal to expected value of y specific, the expected value over all data sets minus h of x squared plus expected value over all data sets y x d minus expected value of y of x and d squared. Okay, now we will call this term bias term and call this variant. Why? Because it means that how much the average prediction of y over all the data sets are different from the h of x, which is the true function of training data. And this actually tells us that how much the prediction of the model is different from the expected or the average value of the prediction of model. So it is kind of variance definition. So we call this variance and call this bias. So we could write the expected loss, which we had in here as bias squared variance plus noise. in which the bias is this and the variance is this, and the noise, as we saw, it is not related to the output of the model. It is related to the true function and the target values. Okay, so maybe it is a little difficult to understand that, but it is very important to have intuition for what you should know is that there is a balance in here. There is a balance between bias and variance. So if you have flexible model, or very flexible model, it means that if we have complex models, flexible models, which means that they could fit on any kind of training data, so they are really complex models. So if we have complex models, it means that the bias, we will have low bias, but on the other hand, because there is a trade-off between bias and variance, then we will have high variance. On the other hand, in rigid models or very simple models, we have low variance but high bias. In other words, if you plot the test error is something like this, and let's call this axis lambda. So we know that the lambda is the coefficient of L2 regularization, or L1, or any term of for regularization coefficient, and we know that it can control how much the model is complex or flexible or rigid. Okay, so when we have very large values of lambda, it means that all of the weights could be very small values, because this term dominates in the loss function. So when we minimize the loss function tries to minimize the values of W to close them as possible to zero. And so it means that the variance of the model, or the fluctuation of the weights over around the zero, is really trivial. So with increasing the lambda, the variance will decrease, while the bias of the model increase. And the bias will be something like this. So this is variance. If making the lambda larger, the variance, or this is actually means that when we increasing the lambda means that we are making the model more rigid. So when we make the model rigid, the variance decreases and the bias increases. So we should just aware of this trade-off between bias and variance. And actually, this is the point that we want to be. In here we have good balance between bias and variance. Okay. Maybe it is better to show you an example from the book. Okay. As you will see, this is the example of polynomial fitting. In here, you will see some different fitted lines over different sample data sets. So different lines means that we have different data sets, we have different samples from the data sets, and we fitted some models on this. As you could see in here, the value of lambda is large. So the variance of the model is very low. In here you could see that the variance of model is low and the bias is high. In here, as you could see, with decreasing the value of lambda, now the variance of model increased and the bias is decreased. And in here you will see that we have a suitable value of lambda in which we actually fitted on the actual line. The green line is the actual line that we want to fit on. So in here we will see that we have the suitable value of lambda. Okay, but the point is that as I mentioned, is that determining lambda is actually kind of hard, specifically when your model is really complex. So when you want to calculate or using the k-fold cross-validation method to determining lambda or holdout method, then you should actually try different values for lambda. So you should train your model for, let's say, 100 values of lambda roughly to get the optimal value of lambda. So this could be computationally expensive for you. For solving this problem, it is really good to somehow we have a way or approach to determining the lambda automatically. This is actually the Bayesian approach. Bayesian approach does that for us, and determining the lambda automatically, as we will see. We don't actually dive into the full details of Bayesian approach, but it is necessary to just have intuition about the Bayesian approach, at least what is it. So, as we mentioned, in Bayesian approach, for the parameters, we just put a prior on the weight vector of parameters. It could be, if the prior is Gaussian, with the mean M0 and the variance S0, then the posterior probability is the T is the training data. So the posterior, so this is the posterior probability over W is so this is interesting. If the prior is Gaussian, then the posterior also is Gaussian, and the M is S and S null verse plus, and you know the phi is our kernel or basis function, and Sn minus 1 is S0 inverse plus beta E transpose phi. And just beta is actually noise precision parameter, or you for now you just think that it is a constant. Noise precision parameter. So it is just a constant now. Now, if we use the maximum posterior probability, then the W, which maximizes the posterior probability, is obviously Mn, because the posterior probability is something like this, and this is M of n. So in here, the posterior probability is maximum. So the estimation of maximum posterior probability is Mn. So if we consider that S null, which is related to the variance of our prior about the weights, is something like this, it means that we have a very broad prior on the weight. It means that approximately we know nothing about our weights, because as you know that covariance matrix this is alpha. This is actually a diagonal matrix. So when you write that in this way, it means that the variance of your weights are very high. So it means that the distribution may be something like this. It's very wide distribution, so we don't know much about the weights. We don't have so much information about the weights. So, and the interesting point is that in that case, the answer of this is equal to the answer of maximum likelihood estimation, because we know that in maximum likelihood estimation we don't have prior on the weights, and actually we don't know the prior on the weights. This is the case when this is the case of maximum likelihood, and with the Bayesian approach, which we don't know a lot about the weights. But now let us consider to that the prior on the weights are the Gaussians. So the P of W even parameter is alpha. Alpha is actually precision parameter. So it is the Gaussian zero mean, and typically we consider that it is zero mean and alpha inverse. In Gaussian distribution, when we wanted to define the Gaussian distribution, we called sigma squared variance. Typically, we call 1 over variance precision parameter, or beta sometimes, because it tells us how much the distribution is precise, okay, over the mean, around the mean, how much it is sharp over the mean. The parameter beta is higher if we have something like this in comparison with something like this. But in this case, we know that the variance is higher. So it is just the inverse of variance. We call it precision parameter. So, okay. Now, in this case, if we calculate the mn is this, and Sn inverse is beta phi transpose phi. So if we take log, it is equal to minus beta over 2 sum, and this actually gives us very interesting result. Squared minus alpha over 2 W transpose W. So as you could see in here, maximizing posterior probability means that because these are minus sign, it means that minimizing, so maximizing this term, it means minimizing this term. So let us factor from beta also. So we have Tn minus W transpose phi squared plus alpha over beta W transpose W. So it means that minimizing this, now this is very interesting result. It means that in Bayesian approach, when we consider Gaussian prior on the weights, so Gaussian prior on the weights with Bayesian approach is equivalent to maximum likelihood or least square plus L2 regularization. As you could see, this is least square terms, and this is L2 regularization with lambda equal to alpha over beta. And the point is that actually we could somehow determine lambda automatically. In other words, for update lambda, we could use maximizing the marginal likelihood function. It is called evidence approximation in machine learning terminology, and for prediction we can write, because when we have Bayesian approach, the prediction is important, because we in maximum likelihood we just have one answer for W, but when we use Bayesian approach, we have posterior distribution over W, not a single point estimation. So how should we predict the single output for the model? We should actually we want the probability of t given the target values. So maybe it is better to write this with another color. So these are training target values. It is equal to times e p of alpha beta given data set target values dw. Okay, and this is the way that we predict the values from the Bayesian model. Okay, actually we will have very other details about the Bayesian approach, but maybe it is not very necessary now to dive into the Bayesian approach now. But if you want to use that in scalar, you could use scalar Bayesian regression. So you will see that here you should actually take a look at the Bayesian regression theory in a very short. So you could see that it consider a Gaussian distribution prior on the output. The obvious advantage of Bayesian approach is that we don't want to set lambda values or regularization parameter. Okay, so as you would see in here, the main advantage of Bayesian regression is we don't want to use the lambda or regularization parameter, and it will be updated in an iterative manner with data. But the disadvantage is that in the inference time, because we don't have a single point estimate, it is a little time consuming because we should calculate this value, which is time consuming and maybe computationally expensive. But for not very large model, it is a very great idea to use Bayesian approach. And Scalearn has some examples about the Bayesian ridge regression. As you could see in here, this is the histogram of the weights. So as you could see in here, it is something like the Gaussian, because we considered and supposed that we have Gaussian prior on the weights. So we have something like Gaussian in the histogram. Okay, and it is better to write this yourself, and if you have any question about how this code works, just ask it on Slack channel. But it is not actually really hard, I think, because it's pretty straightforward. The main thing is going on in here, and this section is just for plotting, so it is not so important. And yeah, just this. I hope that in this session you learned about what is the main difference between the Bayesian approach and the least square approach, and when the least square and or maximum likelihood approach is equivalent to Bayesian approach. Again, the Bayesian approach with Gaussian prior on the weights in linear models, it is equivalent to the maximum likelihood with L2 regularization. It is one of the main reasons of using L2 regularization in linear models. You probably see that a lot, even in nonlinear models. For example, in neural networks or in deep learning models, we will use L2 regularization or weight decay term, and because it seems that it is a reasonable prior on the weights in Bayesian perspective on the weights to have a zero mean and being a Gaussian for the distribution of the weights. So yeah, that's it. And in the next 4 or 5 sessions, we will brush up our skills in Python, and we will see an example in Kaggle how to sign up in a challenge and apply our learned model until now in that challenge, and how to apply that on real data sets. So hope to see you. Bye.